Hey, welcome back to Fat Mama Physics. In this video, we're going to do more half-life examples. So 5, 6, and 7 from 7.03, which is dealing with half-lives. Okay, so let's go. Example 5. There are 5 grams of iodine 131 remaining in a sample after 40.35 days. Oh, so this is the remaining. So, okay, so this is the parent nucleus. It's not the daughter. Meaning, that's why it's remaining. It's not created or produced. How many grams of iodine 131 were in the original sample if its half-life is 8.07 days? Okay, so this is similar to a question we've done before. Because we know the half-life. We know how many days have progressed. We just need to know how many half-lives have occurred, so we know how many times to halve, or actually, this is not how many times we need to have. This is the amount of times we need to double 5 grams because this is the remaining sample. It is the product, what is left over after how many half-lives. So anyways, let's figure out the number of half-lives first. This is going to be 40.35 days divided by 1 half-life, which is 8.07 days. And I predict that's going to look like 5. Yep, that's exactly 5 half-lives. 5 is a likable number, I suppose. So, essentially, if you think of it this way, this is the original sample. The original sample divided by 2 is going to, divided by 2 5 times is going to give us 5 grams, okay? So this divided by 2, so, okay, it's going to give us this, okay? So, this is kind of the dragged out long way of showing you this. But essentially, you start off with some sample, okay? There are 5 half-lives, which means this divided by 2, which will give you this, divided by 2 again, 2 again, 2 again, 2 again, 5 times. So 1, 2, 3, 4, 5. We half it 5 times is going to give us 5 grams. So to go the opposite way, we have to double 5 grams 5 times in order to figure out what the amount of the original sample. So we could do it this way. So we double 5 is going to give us 10. We double 10 is going to give us 20. Double 20 is going to give us 40. Double 40 is going to give us 80. Double 80 is going to give us 160 grams in total. So this is kind of a very simplified way to help you figure out that your grand total is going to be 160 grams. Okay? So another way you can do it is... I'm out of space, so maybe I'll write it here. Oof, I need more space in the next question too. So let's write it here. Okay, so essentially you know that 5 grams is the remaining, it remains after some number times 0.5 5 times. Okay, so to figure out that, you had to divide 5 by 0.5 to the power of 5. So if you put that in your calculator, you're actually going to get 160 grams. Okay, so that is the another way you can do that, writing out an algebraic statement. Okay, so on to example 6. Suppose the ratio of a radioactive parent isotope to a stable daughter isotope within a rock sample is 1 to 7. The half-life of the parent isotope is 710 million years. How old is the rock sample? Ooh, okay. So a 1 to 7 ratio is the result of that many half-lives. So we kind of have to be careful of our interpretation of a half-life, or sorry, of a ratio, my bad. Because what that means is keep in mind the fraction, whenever we deal with fractions, it's dealing with the total. This doesn't give us the total, it gives us parent to daughter. So if we add parent to daughter, that's going to give us a total of 8 parts. Okay, that's a total of 8 parts. Meaning the parent takes 1 part of the 8. Okay, the parent takes 1 part of the 8 equals parent. Okay, so that's essentially a fraction of the sample is now parent. In fact, 1/8 is in fact 3 half-lives. Okay, so 1/2 to the power of 3, or times itself 3 times, is essentially 1/8. So based off this ratio, we're able to figure out the number of half-lives, which is 3. So that's the concept of the ratio. Just be very careful. It doesn't mean 7 half-lives have occurred or anything. It's that it's the ratio of parent to daughter. So the whole sample is parent and daughter. So you have to add the 2 parts together to get a total of 8 parts. Okay, so for 3 half-lives, okay, so we know that the half-life is 710 million years. So we have to multiply 710 million years by 3 half-lives to give the age of this rock sample. So this times 710 is going to be, hopefully, 2.13 billion years. And this gives me 2130 million years, which is going to be equal to 2.13 billion years. Okay, it's just a order of 1,000 again. Okay, so there we go. That's that example. We have one more to go. Example 7. Okay, the activity of a sample is 15 decays per minute. So that's an activity. I'm going to use black for this. The activity is 15. But it's decays per minute, not decays per second. May not matter here, but this is going to be decays per minute. Okay, the half-life is 30 minutes. Predict the time when the activity was 60 decays per minute. So one thing we have to realize is that the decay, the rate of decay, the activity slows down over time because you're going to have less parent radioactive nuclei to decay. So when the activity was 60 decays per minute, it means it was earlier in time. So we have to figure out that how many half-lives have occurred from 15 decays per minute to 60 decays per minute to predict how long, or predict the time when this activity was 60 decays per minute. So a half-life in terms of activity means that every half-life, the activity will half itself. So if we go back 1 half-life, okay, let's write this here. 15 decays per minute. I'm going to write it like that. It looks really bad. But 1 half-life ago, 1 half half-life. I'm going to put 1 half-life as L as life. 1 half-life. So actually, you know what? Since 1 half-life is 30 minutes, let's put 30 minutes. Okay, 30 minutes ago, the activity was twice as high. So that would have been 30 decays per minute. Okay, that's not quite 60 decays per minute. If we go back another half-life, which is another 30 minutes, then the activity would have been double that, which is 60 decays per minute, which means the total time, it has been a total of 30 plus 30, which is total of 60 minutes before when the decay rate was 60 decays per minute. Okay, so 60 minutes total is the time before of which the activity was 60 decays per minute. Okay, or 60 minutes earlier. Okay, there you go. So notice there's not a lot of hard math. It's really working with your understanding of what half-life is. Okay, so again, if you need more practice, make sure you get in the practice. I wish you the best of luck. Thank you for watching, and Fat Mama Physics signing out.